In this video, we're going to look at sequences and whether sequences converge or diverge. And here we're talking about the nth term, the last term. So will it converge or diverge? Do not get this confused with series. This is a sequence. So we've got this sequence that is in brace notation, and our particular textbook, Anton, uses brace notation. So we have the general term, 5 to the n, divided by n factorial, and we want to know, does it converge, or show that it converges, and find its limit. Well, our favorite test for that, our number one test, is ratio test. So let's go ahead and do the ratio test. Remember, the ratio test is a sub n plus 1 divided by a sub n. So we need the next term provided by the initial term. So let's go ahead and start off by going 5 to the n plus 1 over n plus 1 factorial. We're replacing all n's with n plus 1 divided by 5 to the n over n factorial. Well, so when you divide fractions, you multiply by the reciprocal. So we've got 5 to the n plus 1 over n plus 1 factorial, multiply by the reciprocal, n factorial over 5 to the n. This is a key step in many FRQs for Calculus BC, so make sure you get in the habit of setting up the ratio and showing the multiplication. From here, we can do a little bit of algebra and some cleanup. 5 to the n plus 1 can be rewritten as 5 to the n times 5 to the 1. n plus 1 factorial can be rewritten as n plus 1 times n factorial. So if we replace those with their equivalents, now we can cancel out an n factorial. We can cancel out a 5 to the n. On the top now we have 5. On the bottom we have an n plus 1. At this point, let's take the limit as n goes to infinity, and let's observe what happens to our nth term, our potential last term. Well, notice this is end behavior, and this is a low-high problem, and a low-high problem is always, always, always 0. So this sequence will converge to 0. Let's take a look at another example. So we want to show that the sequence with the nth term, again, the nth term is the general term, we want to show that this converges. Well, since they gave us the nth term, we can use limits for this, and that's a fairly basic limit problem. Limit as n approaches infinity of n over 1 minus 2n. Again, this is end behavior, so we can use high-low, low-high, same-same. This is a same-same, so we look at the coefficients. Coefficient in the numerator is 1. The denominator, if we ignore the 1, would be negative 2. So this series, or this sequence, converges to a negative 1/2. Let's take a look at another one. So does the nth term converge or diverge? Again, to answer that question, we can use limits for that. So let's go ahead and take the limit as n approaches infinity of n squared over 2 to the n minus 1. Well, so if you remember what I taught you about AP and one of its favorite tricks, first of all, we can, for the moment, ignore the negative 1. We learned that when the variable is in the exponent, it's going to get bigger, much larger than if you simply take something and square it. So this ends up being a low-high. And a low-high always, always, always converges to 0. Sorry, I got distracted by someone at the door. Now, let's pretend that we forget that. Well, if we forget that, then, when we plug in our infinity into this problem, because we've forgotten this, we get infinity over infinity. Well, anytime you get infinity over infinity, you could use L'Hopital to help us. So let's do a L'Hopital on this and see what happens. So if I rewrite this as the limit as n approaches infinity, if I do L'Hopital, the derivative of the top would be 2n. Derivative of the bottom, well, that's an a to the n problem. So if I do a to the n, I would get 2 to the n natural log of 2. Well, so if I plug in again, once again, I get infinity over infinity. So I can L'Hopital again. If I L'Hopital again, limit will go to infinity, then the top becomes a 2. The bottom, well, let's see, this is going to be a product rule, so we could go first times derivative of the second plus the second times derivative of the first would be 2 to the n natural log 2. So we end up with, on the bottom, 2 to the n natural log of 2 squared. Well, now, as we're going to infinity with our n behavior, we certainly have a low-high, and this is going to go to 0.